Hey guys, so this video on the STEM Spot and the chemistry series is on dimensional analysis. So to give you a general idea of what this video will include, I'm going to start with a general definition of dimensional analysis and then show you some simple and small applications that dimensional analysis has. And then I'm going to move into more I wouldn't say difficult, but more involved problems from the AP Chemistry free response questions that are released online. So I went through previous years and I found different questions that use dimensional analysis, and we'll just work through those so you get a feel of the AP Chemistry test, and then you'll also be applying this new concept that we learned. So I'm going to start with a general definition of dimensional analysis. It's super simple. It kind of sounds like a scary name, but it's honestly a really simple concept. You're basically going from one unit to another unit. It's basically a conversion, if you will. An example, going from inches to feet, meters to miles. That's basically what we're doing here. You're just trying to make equivalent values, and then you're going to use those equivalent values to convert. And I'll show you what I mean by that. So let's say we had this value of, that's an eraser. We have this value of 5.0 minutes. So say I wanted to convert these 5.0 minutes to seconds. So the first step that we're going to think about is, well, how do I get to minutes to seconds? So if we're saying minutes to seconds, how am I doing that? So we're going to think, how many minutes are in a second, or how many seconds are in a minute? I think the most commonly known conversion between minutes to seconds is that there are 60 seconds in 1 minute. Right? So we could also say 60 seconds equals 1 minute. So this is like an equivalent statement that we have, and we're going to be using this to convert our 5 minutes into seconds. So whenever you're doing a dimensional analysis problem, especially when you're first starting to learn the concept, it's really important to make these little equivalence statements so you understand how the two different units relate to each other. So if we're going from minutes to seconds, what we're going to do is we're going to make a little conversion fraction, I like to call it. So if we're trying to convert from minutes, we're going to put minutes in the denominator so the minutes cancel out, and we want it to be in seconds, right? And then we're going to put the 60 up here because there's 60 seconds in 1 minute. The way I like to think about this as well is 60 seconds is equal to 1 minute, as we mentioned. So say 60 seconds is x is equal to 1 minute, which is also x because they're equivalent values. If we put x over x, we get 1. So we're just essentially multiplying by 1. We're not doing anything to this 5 number. We're simply just converting it. So that's one way to look at it. And you always want to take whatever unit is up here, the unit that you're trying to get rid of, and put it in the denominator to cancel it out while you have your new unit on top. So now we're doing 5 minutes times 60 seconds over 1 minute. Our minutes are going to cancel out because you're dividing them. You're taking that minute on top and putting that minute in the denominator, and you're canceling them out. And then we just have 5 times 60. And for a lot of dimensional analysis questions, you can have a calculator with you. Obviously, this is a little more simple, but then we would have 300 seconds. And then, as we learned in our last video with significant figures, conversion factors actually don't have any significant figures. They have infinite significant figures because they're predetermined values. It's not like we measure there's 60 seconds in 1 minute. It was predetermined. That's like a known value. So there is infinite sig figs. So keep that in mind. So it's not like there's one sig fig or one sig fig here. these are infinite. They don't have any effect on our final significant value. This is what dictates our final significant values. And because there's a 5.0, there's two significant values, or, two significant figures. So it's not going to be 300. Well, it is going to be 300, but here we're only portraying one significant figure. So let's just do that so you can see that this would be our answer. Or we could put it into scientific notation and call it 3.0 times 10 to the 2 times 10 to the second seconds. And then we have 2 sig figs here, and we have 2 sig figs here. Okay, perfect. So then there's our answer. We got 300 seconds with 2 significant figures. So there's like a lot happening here, but I just wanted to explain some commonly confused ideas. So we're going to do one more really simple one, and then we'll start with the actual College Board released AP Chemistry FRQs. So let's do one more. We can do, we could do inches to feet. So say we have this really big number, 32510 inches, and we want to get this into feet. So we're saying inches to feet. Let's make an equivalence between the two. How many inches are in 1 foot? Well, there are 12 inches in 1 foot. Okay. As we did before, the inches is going to go in the denominator and the foot is going to go in the numerator. Then we're going to divide. We're going to have our 32510 divided by 12. Okay, we have this irrational number. So let's take a look at how many sig figs are here. There are 4 sig figs. So let's retain 4 sig figs in our final answer as well, 2709 feet. Don't forget your units. And then there we have our answer. So dimensional analysis is really just you're taking a look at this and you're applying it to your initial value. So I've shown you some examples with very simple conversion factors, whether it's inches to feet or whether that's seconds to minutes. Those are all simple conversion factors. You're gonna need to know more complex ones, and I will include a list of those at the end of this video. That's gonna be something important because you're gonna face a lot of different conversions, and oftentimes you're gonna have a lot on your formula sheet, but sometimes you won't, and sometimes you'll have to memorize these things. But I think a majority of them, I don't think there are many really off the conversion list that's on your formula sheet on the test. So that's that should make you feel better. You don't have to do too much memorization with this, but it does make your work a little bit faster. So yes. Okay. Now it's time to look at the actual AP Chemistry questions. Okay. So here, in a separate experiment, the student is given a sample of powdered iron that contains an inert impurity. The student uses a procedure to oxidize the iron in the sample to Fe2O3, or iron 3 oxide. The student collects the following data during the experiment. We have some data. Okay. Part G, we're looking at Part G from the AP Chemistry FRQ from 2018 if you're looking for this. So this question seems a little more involved, and that's because it's part of a lot of other parts, but we're just going to be simply looking at the dimensional analysis part of this. So we're just asked how many moles of Fe are in the Fe2O3. So let's foresee how much Fe2O3 do we have. So it says here mass of Fe2O3 produced is 7.531 grams. So let's just write that down, 7.531 grams of Fe2O3. So moles, we're going to get this grams into moles. Okay, So if you're unaware of the conversion from grams to moles, we're simply just going to be looking at the molar mass. So here, hold on. I don't know Fe2O3's molar mass off the top of my head, but you can calculate it using a periodic table. I'm just going to simply search it up right now, but yeah, you can definitely calculate that using your periodic table, using the molar masses. So we're going to have a molar mass of 156.69 grams in every 1 mole of Fe2O3. Okay. Then, now we're trying to get it into moles of Fe. So looking at Fe2O3, in 1 mole of Fe2O3, how many moles of Fe are there? Well, looking in 1 mole, we see 2 moles of Fe. So you're just looking at that subscript, and that is the exact units that we want our final answer to be in. So now let's do 7.531 divided by 156.69 times 2. And that will give us a really small number. And let's take a look at these sig figs here. There are 4. So we want our answer to be in 4. So 0.09613. This is rounded up. Moles of Fe. Perfect. That's really all there is to that. Okay, we're going to do one more question. Here, this one is from 2022. And these are all on the College Board website. If you search up AP Chemistry released FRQs, you'll find these there. Okay, let's take a look at this. So a student reacts 0.300 grams of methyl salicylate, and it gives you the formula there, with a stoichiometric amount of strong base. This product is then acidified to produce salicylic acid crystals, and it gives you the formula there. For every 1 mole of methyl salicylate, and we're given the molar mass, so we don't have to calculate that or anything, which is the reactant used, 1 mole of salicylic acid crystals is produced. Calculate the maximum mass in grams of, this is our salicylic acid crystals, that could be produced in this reaction. So we're already given an equivalent statement here. It sounds a little complicated, but it's really not. So we're saying for every 1 mole of C8H8O3, we will have 1 mole of HC7H5O3. And that's all from this part here. So now it's asked us to find the maximum mass in grams that can be produced in this reaction. So let's look back up here. So we see a student reacts 0.30 grams of methyl salicylate, and then we're trying to get it into the grams of the crystals, right? So let's start off with this 0.300 grams. Just safe tip for anybody out there, if you're not sure where to start, literally just find that reactant number and just run with it. If I don't know what I'm doing, I'll just start with that number and then I'll run with it and see where I go. Usually I'm able to find my way through the dimensional analysis when it gets really, really long, but that's my tip. Just once you see the number, just write it down and start converting, basically. So we have 0.300 grams of C8H8O3. Okay. Then once again, we're going to be doing that conversion from grams to moles. So here we're given the molar mass of C8H8O3 or methyl salicylate, and that is 152.15 grams of C8H8O3 per every 1 mole of C8H8O3. And then we're going to be referring back to this equivalence factor right here that we have. So in every 1 mole of C8H8O3, we have 1 mole of HC7H5O3. Okay, and then now we want, remember, mass in grams. Mass in grams, right? So we need the molar mass of HC7H5O3, which is given right here. So in 1 mole of HC7H5O3, we have 138.12 grams of HC7H5O3. It's kind of repetitive writing it out over and over again, but it prevents you from making mistakes. Okay, and let's do this whole crossing out. You know, we may have forgotten to do some crossing out here. It's the most fun part, and you're double checking to make sure that you got all your units right. So, grams, moles, final answer in grams. So now we get to plug this all into our calculator. So let's do that. 0.3 divided by 152.15 times 1 times 138.12. Okay, and we're given a pretty small number, but that makes sense as we started with 0.3. And we had, let's count how many sig figs. 3 sig figs. So now we have 0.272 grams of HC7H5O3. Okay, that's the final answer for this question. So if you want to refer back to these questions, it's just the 2022 and then 2018 FRQs. So yeah, that's it for this video on dimensional analysis. I hope it was helpful. I hope it gave you a general idea of what dimensional analysis is and you were able to see it in an actual AP chemistry light. Definitely continue to practice this as it can be tricky for some people, but the more practice you do, the easier it'll get. So just remember those equivalence factors and you should definitely be good. So thanks for watching.